Hey everyone, and welcome. Right then, let's dive straight into some GCSE Physics revision, focusing on a really important topic, the turning effects of forces. We're talking moments, levers, and gears, all from section 4.5.4 of the AQA spec. My goal is to get you feeling super confident for your exam.
But before we get into the nitty-gritty, let me ask you something. Have you ever stopped to think about a door? Why is the handle always on the side furthest away from the hinges? It's not a design choice. It's pure physics. And trust me, by the end of this, you'll see doors in a whole new light.
So here's the game plan. We're going to start with what the turning effect actually is, then we'll get into the maths and learn how to calculate it. After that, we'll uncover the principle that makes things balance, we'll tackle a proper exam-style problem together, and finally, we'll see how it all connects to amazing things like levers and gears.
Okay, first up, the turning effect. Now, we're used to thinking about forces as just, a simple push or a pull in a straight line. But forces can do something else, something really cool. They can make things rotate around a fixed point, which we call a pivot. And that rotation is exactly what we're diving into now. And this turning effect has a proper physics name. It's called a moment. Simple as that. This definition is your foundation for everything else, so pop it on a flashcard. A moment is just the turning effect of a force. It's how we measure the oomph of a force's ability to cause a spin.
Okay, so you've got the definition down. Awesome. But in physics, we love to put numbers on things, right? And your exam is definitely going to ask you to calculate the size of a moment. The good news? There's a really neat formula for it.
And here it is. This is one to commit to memory. The moment of a force is simply the force multiplied by the distance from the pivot. M equals F times D. It's clean, it's simple, and it's incredibly useful.
Now let's break this down, because the details here are where people often slip up in exams. Move, the moment, is measured in Newton meters, F, the force, is in newtons, and D, the distance, is in meters. But look at that word in caps, perpendicular. This is so important. The distance has to be at a right angle to the force. Think of it this way. If you push on a door straight towards its hinges, it's not going to turn, is it? You have to push at right angles to get that swing. That's the perpendicular distance, and it's a classic exam trip-up, so don't fall for it.
All right, so calculating one moment is sorted. But what about in the real world where things are a bit more complicated? Like a seesaw at the park with kids on both ends. How do you get it to balance perfectly? Well, for that, we need the principle of moments.
And this right here is the golden rule, the law of the land for balancing things. It comes straight from the AQA spec. It just means that if something isn't spinning, then all the turning effects trying to make it go clockwise are perfectly canceled out by all the turning effects trying to make it go anti-clockwise.
And this just lays it out so clearly. Think of it like a cosmic tug-of-war around a pivot. You've got the anti-clockwise team on one side and the clockwise team on the other. For the object to be stable and balanced, what we call being in equilibrium, the two sides have to be pulling with exactly the same strength. They must be equal.
Okay, theory's great, but let's see how this actually works with a proper exam-style question. This is where you really get to show the examiner you know your stuff. We're going to do this just like you would in the real exam, step by step.
So here's our scenario. We've got a 40-Newton weight and it's sitting 2 meters away from the pivot. That's creating an anti-clockwise turning effect. Now we want to balance this out using a heavier weight, 80 newtons. The big question is, just where do we need to put it to make things level?
Here is how you get full marks every time. Step 1, and this is super important. Always state the principle first. Clockwise moments equal anti-clockwise moments. Step 2, work out the moment you already know. That's the anti-clockwise one, 40 newtons times 2 meters, which gives us 80 newton meters. Step 3, set up your equation. Because it has to balance, we know the clockwise moment must also be 80 newton meters. So our 80 newton weight times some unknown distance d has to equal 80. And finally, step 4, solve for d. Just rearrange the equation. d equals 80 divided by 80. So the answer is 1 meter. See? Totally manageable.
So, we've balanced a seesaw. Big deal, right? Well, actually, yes. It's a huge deal. Because this exact same principle is the secret behind some of the most useful machines ever invented by humans: levers and gears. This is where the physics gets to work.
Both of these incredible inventions are all about taking this turning effect and putting it to work for us. They use the principle of moments as a clever trick. By playing with the distances from the pivot, we can use a tiny little force, applied a long way away from the pivot, to defeat a huge force that's much closer, just like we saw in our calculation.
And this is the magic trick, the whole point of using them. Levers and gears are what we call force multipliers. They let you swap distance for force. So you might have to move your hand a bit further, but in return, you get this massive boost in force that lets you do things that would otherwise be impossible. It's how a crowbar lifts a heavy rock, or how you can pedal up a steep hill on your bike.
And that brings us full circle right back to that door handle. A door handle is a lever. You apply a small force far from the pivot, the hinges, to create a moment big enough to turn the latch inside. It's genius. So now that you get the principle, start looking for it. It's everywhere. A bottle opener, a pair of scissors, a wheelbarrow, all using moments to make life easier. What will you spot next?